Welcome to section 5.5, counting techniques. We're going to be learning how to count.
So this is going to be helpful when we're doing the classical method,
the number of
calculating
events
probability.
Because
with classical probabilities, we count up the amounts of events and we count up the number of observations in a sample space. And so far we've been working with small sample spaces, small events, but after 5.5 we can look at much larger sample spaces. All right, so the first type of technique we're going to learn about is the sequence of choices. All right, so the example we're going to use is going out to dinner. So when we go out to dinner, we have a sequence of choices. We can choose the appetizer, then we choose the meal, and then finally we choose the dessert. So we make three sequence of choices. All right, and in this particular one, we have 4 appetizers. We can choose from 5 meals. We can choose from 3 desserts. So we want to know how many different possible combinations can we have for dinner. Okay, so let's draw a picture to illustrate this. Let's draw our 4 appetizers. Let's say they come out on these rectangular plates. Okay, I'll just say A for appetizers. And so far we have 4 choices. All right, so we can choose from those 4 appetizers. Next comes the meals. So we'll do round or circular plates for that. And there's 1, 2, 3, 4, 5 meals. And I'll just use the letter M. All right, and consider this. So let's say we chose this first appetizer. This first appetizer can be paired with 1, 2, 3, 4, 5 meals. So just with that first appetizer, we have 5 combinations. All right, so with this first appetizer, we're going to have 5 combinations. And then what about the second appetizer? Well, again, we are going to get 5 combinations with the meals with that appetizer. And same with the third and the fourth. All right, so how many combinations just with appetizers and meals do we have all together? Well, we have 5 and 5 and 5 and 5. So 5 plus 5 plus 5 plus 5 choices. So far we have 20 combos just with those first 2 rounds. And what's a shortcut way of writing 5 plus 5 plus 5 plus 5? Yes, let's do the grown-up math version. And that's 4 times 5. All right, so 4 appetizers. Here, let me color coordinate too. 4 appetizers, so blue, for 5 meals. Okay, let's talk about the desserts, and we'll bring out maybe a green triangle for desserts. We have 3 desserts. 1, 2, 3 desserts. And each of these desserts, you can think of combining the 20 combos with that. All right, so we can take all the 20 combos and pair them with the first dessert. Or we can take those 20 combinations and pair them with the second. Or we can take the 20 appetizer meal combos and pair it with a third dessert. So how many do we have all together? We have 60. 20 plus 20 plus 20 is 60. So we saw that as 3 times 20, 3 for the amount of desserts. And remember that 20 came from the 4 times 5. Okay, so let me finish all my color coordinating. So to figure out how many sequence of choices we had, we took the 4 appetizers times the 5 meals times the 3 desserts. And that's how we got our answer, which was 60 combos of the appetizer, meal, desserts. So when this person goes out to dinner at this restaurant, they have 60 different combinations to choose from. All right, so sequence of choices, we're essentially just multiplying the amount of choices we have for each selection. So let's write that out technically. Here's the technical definition. So let's set it up. If a task consists of a sequence of choices, whoops, in which there are P selections for the first choice. So in this case, there was 4 selections for our first choice. Q selections for the second choice. In our case, we had 5 meals, 5 selections for the second choice. Our choices for the third, we had 3 choices for desserts, the third choice. All right, so are we seeing this pattern? We can go on forever. Then, let's switch inks. After we do that, then the amount, or then the selections can be made in and again, we multiply the amount of options for each selections. And again, we just carry that out for however many selections there are. And we can do that in that many different ways. All right, so there you go. So this is also going to be handy to develop more methods, more techniques of counting. But first, before we see that, let's look at an example. So how many different license plates can be made by using one letter followed by 5 digits, selected 0 through 9? All right, so the license plate has one letter. Whoops. Here's a letter. And then we have 5 digits. So 1, 2, 3, 4, 5. And then these are our digits. Okay, so it's a sequence of choices. First we choose the letter, then we choose the digit, then we choose the digit, then we choose a digit, then da-da-da-da-da-da. Okay, so it doesn't say anything like the digits cannot repeat, so we can assume they repeat. So just think of a license plate number. Do you ever see the same number more than once? Yes, it happens all the time. Okay, so how many letters are there? How many choices do we have for that first one? We have 26 letters. And if we're choosing digits 0 through 9, how many digits is that? Good, we can choose from 10 digits for each of those 5 choices. All right, and so our new multiplication rule tells us that we are going to multiply all of these together to see how many different license plates we have. And multiplying by 10 is nice, so we can just add a 0. So it's going to be 26 with 5 zeros. Come back and do our commas. So 2.6 million different license plates. Crazy. Okay, so that's a pretty straightforward example. Let's see how our multiplication rule of counting can give us different techniques of counting. So let's consider this situation. We're going to be arranging magazines on a table. And we're going to start with 5 magazines, and we want to arrange them on the table. Okay, and there's different ways to arrange the magazine. Maybe your favorite is on the top, maybe your favorite magazine's on the bottom, maybe your favorite magazine is in the middle. All right, so essentially, we have our initial spot on the table, and before we place the magazine down on the table, we have 5 magazines to choose from. All right, so let's draw our picture first. So let's draw our arrangement. So let's say we're arranging our magazines like this. 1, 2, 3, 4, 5. All right, very artistic. Okay, so when we look at our very first spot, so we would put the bottom one down first, we have 5 magazines in our hand, so we have 5 magazines to choose from that bottom spot. And then the next magazine, we have 4 magazines left in our hand, so we have 4 to choose from. Then we have 3 magazines to choose from. Then we have 2 magazines to choose from. And then the very last magazine, there's only 1 magazine left in our hand. So of course there's only one way to do that. So this arrangement, and I'm going to highlight that word, arranging, this arrangement is a sequence of choices. So again, how many different ways can we do this? We had 5 to choose from the first slot, and then 4 times 3 times 2 times 1. Okay, and then if we do all that multiplication, we're looking at 120 arrangements, 120 arrangements. Okay, so this is going to be an important lesson for us, and we're going to be using this often. Like essentially when we start with a number and we multiply down all the way to 1, and we use it so often that we give it a special math symbol, and it's an excited 5, 5. And we also read it 5 factorial. Okay? So for instance, just look at another example. If we had 7 magazines and we wanted to arrange all the magazines, it would end up being 7 factorial, which is 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, so in general, formulas are always nice and nice to generalize. So factorial, we start at that number, and then we multiply everything, just going 1 down from that number until we hit 1. Okay, so a couple things I want to note that come up with factorial, especially in this chapter. 1 factorial is defined to be 1. 0 factorial is defined to be 1. Can you believe that? All right, and 0 factorial is 1 because if it was 0, it would mess up some formulas that we're going to see soon. All right, so something that we can also do, let's do our magazine example again. But let's say we have 5 magazines, but we just wanted to pick out our top 3. We just wanted to arrange 3 of the magazines. So again, this bottom one, in our hands, there's 5 magazines, so we'd have 5 choices to choose from, and then 4 choices, and then 3 choices. All right, so the amount of arrangements we have, 3 out of 5 magazines, is 5 times 4 times 3. We have 60 arrangements this time. Okay, so let's examine that for a little bit. 5 times 4 times 3 was almost like a factorial, right? Except it didn't have the times 2 times 1. So when we're talking about crossing off things in math, check this out. That's kind of the same as canceling, right? So we can actually cross out by dividing out those factors. So now look what we did, and we're working our ways towards a formula, so that's what we're doing here. So the top is 5 factorial. 2 times 1 is the same as 2 factorial. And look at 3 out of 5. How does 2 relate to 3 out of 5? Or 3 and 5, I should say. We can subtract 5 minus 3. Okay, so what the purpose of this little discussion here right now was to lead us to a formula. So when we're arranging things, the grown-up math word for that is a permutation. So a permutation is an ordered arrangement. in which our objects are chosen from n distinct objects without repetition. So in this example, it was like 3 objects were chosen from 5 distinct magazines. And notice the order mattered, because your favorite magazine could be on the top, your favorite magazine could be in the middle, your favorite magazine could be at the end. All right, and then the notation we use is this, P for permutation. And in our previous example, we would have written 5 magazines, P, 3, and we said that this equaled 60. So that's the notation. So in order to use a permutation, we have to check 3 things. We need n distinct objects. So in other words, all of the magazines were different. They weren't the same issue. They were all different magazines. No repetition. That happened naturally. We can't have our favorite magazine on the top and at the bottom at the same time. That's impossible because we have distinct objects. And then the big one, that's really the one we're going to focus on, is the order is important because it's an arrangement. So that's also a key word. Order is important. Okay, so if we check out this formula, let's go back up here. We said that this was 5 permutation 3, okay? Here's our n amount of objects, and we chose 3 of them, okay? So let's go back down, and we have a formula for permutations now. Here's our formula. If we have n PR, those n and r's are subscripts, by the way. This is going to be n factorial divided by n minus r factorial. All right, so let's look at an example with this. So we want to know how many ways can horses in a 10-horse race finish first, second, and third. Okay, so before I scroll away from this, do we have distinct objects? Yes, we have 10 distinct horses. So let's just write out a checklist. We have 10 distinct horses. Is there repetition? Can a horse be first place and finish third place? No. Is order important? Absolutely. Is there a difference between the gold medal and a bronze medal? Yes. So order matters. So all of these things tell us that we have a permutation on our hands. So all of these things tell us that we have a permutation. So we're going to use our formula. Permutation. Okay. So what's the n? How many objects are we dealing with? We have 10 horses. How many are we going to arrange? 3 for first, second, and third place. So it's going to be a 10 PR. So according to our formula, it's 10 factorial over 10 minus 3 factorial, which is 7 factorial. Okay, so one way that's helpful to do these factorials, I like to rewrite the top, the numerator, in terms of the bottom factorial. So in other words, this is how I would write this to solve it. I would write, I'll start down here, 10 times 9 times 8. And now instead of writing 7 times 6 times 5 times 4 times 3 times 2 times 1, that's the same as 7 factorial. Here, let me write that in yellow. That's the same as 7 factorial. And now I'm going to divide that by the denominator, 7 factorial. And now I can just cancel the 7 factorials. And now this is just the calculation, 10 times 9 times 8. So how many different combinations of first, second, and third will there be? 720 different ways. There you go, getting it on the border right there. All right, so we did our permutation. I also wanted to show you an alternative way to solve this too. This can also be thought of as a sequence of choices, right? How many choices do we have for first place, second, and third? All right, well, how many horses do we have before someone finishes? There's 10 different horses. Now, how many are left for second place? 9 horses. How many are left for third place? 8 horses. 10 times 9 times 8. Does that sound familiar? That's what we got for the permutation. So again, we get 720 different ways. All right, so everything's pretty consistent with that, so that's good. All right, so let's talk about when order does not matter. All right, so order does not matter for sampling, for instance. It doesn't matter when we're talking about groups of people coming somewhere. So that's where we're headed to next. Order does not matter. And when order doesn't matter, we use combinations. We're more interested in the combination of people. So the definition starts off the same. It's a collection of R objects that are chosen from n distinct objects. And the big thing that's different from a permutation is order does not matter. And we even have a similar symbol. Okay, so let's do the same thing as before. So just as before, we have n distinct objects. No repetition, as before. And then the big one, order is not important. Permutation is just order is important. So that's the difference between permutations and combinations, is that word right there. All right, and then of course our formula. It's really similar to permutations. We start off the same way, actually. But we get a lot of repeats. For instance, let's say we're talking about groups of friends coming to the park with us, and we have John, Alan, and Paul. Well, taking John, Alan, and Paul is the same thing as taking Alan, John, and Paul, Alan, Paul, John, Paul, John, Alan, Paul, Alan, John. All right? It's all the same group of people. So permutations, we would count every single one of those as something different. But when we're talking about combination, when we're interested in the group, we get a lot of repetition. And it turns out we get our factorial many repetitions. So this is our formula for combinations. All right, let's head on down to an example. And it's something similar, taking a group of friends somewhere. So suppose I have 5 friends, and that happens when you reach your 30s. And I want to take 2 to the movies. How many different combinations of friends could I take? All right, so again, we're talking about groups and combinations of friends. So we have to find these key words in this section, or else this section is going to be challenging. So groups is a combination. So out of the 5 friends, we're going to choose 2. All right, so again, it's a combination too. Just, you can think of this in your head. If you have Sally and Mary, taking Sally and Mary to the movies is the same thing as taking Mary and Sally to the movies. You guys are going to tell the same jokes. You guys are going to have the same stories. It's the same group of people. So our formula is 5 factorial over 2 factorial times 5 minus 2 factorial. All right. So we have this, okay? And we can fool around with it. I'm going to try to get rid of the bigger factorial on the bottom. And I can do that by writing the top in terms of 3 factorial. I'm just going to expand 2 factorial while I'm at it. It's just going to be 2 times 1. Let's get to canceling. 3 factorials go away. 4 and the 2, we have a common factor of 2. So we're left with 5 times 2 on the top and 1 on the bottom. So we have 10 different groups. Okay, so why don't you guys go ahead and try out example 3. You guys can push pause, and then we'll see how you do. Okie dokie. So simple random samples. We want to know how many different simple random samples of size 4 can be obtained from a population whose size is 20. So same thing, we're more interested in the group of individuals. It doesn't matter if we have A, B, C, D, or D, A, B, C, C, A, B, A, D, excuse me, anything like that. So we're taking the whole group. Order does not matter. So is that permutation or combination? Combination. Okay. Here we go. This is going to be 20 factorial over 4 factorial. 20 minus 4 is 16. So I'm going to rewrite the top in terms of 16. Like this. I'm going to expand 4 factorial as well. And then I have 16 factorial that I'm going to cancel. What else can we cancel? Well, let's see. 20 over 4 is a common factor of 4. 3 times 2 is 6. And there's a factor of 6 in the 18. So we're looking at 5 times 19. Let's rewrite this. So we're looking at 5 times 19 times 3 times 17. All right, so I'm going to get my calculator out, and we'll see what you guys do. So how many samples do we have from that population? 4,845. All right. Excellent. Okay, so let's go on to our final counting technique, and then we'll start calculating some probabilities. We are going to be going and looking at arrangements of non-distinct objects. So permutations and combinations, it's distinct objects, right? Distinct horses, distinct individuals, distinct friends, distinct magazines. But check this example out. Let's say we have flags, and 5 are white, 3 are blue, and 2 are red. Those 5 those 5 white flags are non-distinct. Those 3 blue flags are non-distinct. Those 2 red flags are non-distinct. So this is an arrangement of non-distinct objects. So we need a different technique. So let's go through this. We'll do our vertical arrangement of flags. So let's draw a vertical flagpole. 5 plus 3 plus 2 is 10. So we're going to be arranging 10 flags. Oh, right there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And our first step is let's choose the position. For 5 white flags. Okay, so out of the 10, slots, we're going to choose 5 of the slots. Okay, so let's make it as random, doesn't really matter. So we can do like 1, 2, 3, 4, 5, maybe something like that. All right, so notice if we were to flip those first 2 flags, it would be the same thing. So how many different ways can we do this? Well, order doesn't matter. It's a combination. All right, so we're going to treat this as a sequence of choices. That first choice has 10C5 many different ways. All right, and then next, we're going to choose the positions. For the 3 blue flags. All right, so how many are left? How many positions are left? 1, 2, 3, 4, 5 slots are left. And how many are we going to fill up? 3. All right, so maybe we would go something like 1, 2, 3. All right, and again, if we switch these 2, it's still the same arrangement. So it's a combination. Order does not matter. So we're looking at this. 5, choose 3 different ways of doing that. Finally, our last sequence of choices, we're going to choose the position for the 2 red. And then look at what we have left. How many ways can we really put in the red flags? There's only one more way to do it. All right, and that's because we have 2 more slots and we're choosing all 2 of them. So 2, 2, 2 is actually going to be 1. All right, so as far as the sequence of choices go, our first choice, so we're going to use the multiplication rule. We had 10 choose 5, and then we have 5 choose 3. And then we had 2 choose 2. Okay, and then let me tell you, if you go back and use the formulas, you're going to be able to cancel a lot of factorials. And this is what you're going to be ending up with. You have the 10 factorial on top for 10 total flags. On the bottom, it's 5 factorial for 5 white flags, 3 factorial for 3 blue flags, and then 2 factorial for 2 red flags. And then that's actually how we derive our formula down here. So permutations with non-distinct objects. And then we have a very similar formula here. And you can relate that formula back to what we have. Okay. So now let's see how this relates back to the classical method of probability. So let's look at this example. In the Illinois lottery, an urn contains balls numbered 1 to 52. From this urn, 6 balls are randomly chosen without replacement. Ooh, I'm going to highlight as I go because I know that's a key word. Without replacement. 6 balls are chosen randomly. For a $1 bet, a player chooses 2 sets of 6 numbers. That's nice. And to win, all 6 numbers must match those chosen from the urn. Ooh, and the order in which the balls are selected does not matter. Great. What is the probability of winning the lottery? Well, let's write some notes. So a lot of information. So again, it's always nice to focus on that last sentence. What is the probability of winning the lottery? So I would write that first. This is what we want to find. Probability of winning. I'm going to take it a step further. We have 2 sets of numbers, right? So that means the probability that the first set of 6 wins or the second set wins. Okay, what is or? What operation is that? Plus. All right, so we're actually doubling our odds with 2 sets of numbers, and that makes sense. Whoops. First set or the second set wins. Wins right here. Okay, so let's break that down a little bit further. So what would it mean to win? So it would mean out of all sets of 6 numbers, because we're pulling 6 numbers, So that's our sample space. Out of all the 6 number combinations there are, the event of winning would be our winning number, 1. That's the probability of winning. And same thing with the second probability, the probability that the second set of 6 numbers win. Well, that means your set of 6 numbers is the event. So there's one in that set in that event. The sample space is all possible combinations of 6 numbers. Okay, so we got to figure out, we got to figure out this. And we can do that by using our counting technique. So first of all, what situation are we in? Okay, so let's go through the checklist. Do we have distinct or non-distinct items? Well, we have balls numbered 1 to 52. Those are distinct. So we have distinct objects. Are we allowed to repeat? No, because they're chosen without replacement. So that means there's no repetition. And is order important or order does not matter? That's this part. The order in which the ball is selected does not matter. So order, not important. Order, not matter. I'll write that. Okay. So is that a combination or a permutation? It's a combination. That's great. And what's your N? It's the 52 numbers. And how many are we choosing? 6. All right, so let's figure this out, okay? So this probability and this probability, they're going to be the same thing, right? Look at it and convince yourself. So it's going to be 2 times that. There's going to be 1 on the top. And all sets of six numbers, that's a combination. It's going to be 52, choose 6. Whew. That is a big number. Okay, so I'm going to tell you what that is. And then in just a second, in the next video, we're going to use our calculator. But don't try to do it by hand. I'll show you on the calculator. If you calculate this out, it ends up being this number. All right, and then it's going to be 1 over that times 2. And you guys are going to get this. You're going to get 9.8 times 10 to the negative 8. All right, and just to give you an idea of what that looks like, it's 9.8 with 7 zeros in front. 1, 2, 3, 4, 5, 6, 7. Okay. Just to put that in perspective about how maybe playing the lottery isn't your best idea for wealth. It's good to have a backup plan other than winning the lottery. If we're talking about the law of large numbers, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9 decimal places. So we need 9 zeros. Okay, so let's see. This is saying, by the law of large numbers, let's see, that's 1,000, that's 100,000, this would be million. So this is billion. If we were to play 1 billion times, if we were to play this lottery 1 billion times, we would expect to win about 98 of those times. All right. So those are your probabilities of winning the lottery. You have to play 1 billion times. And then you can win 98 of those times. All right, so let's see how we're going to do all of this on our calculator in the next video.